All right, so today we're going to be starting chapter 21. So we're going to start actually calculating magnetic fields and seeing how magnetic fields are actually formed now. So the first thing, I want to go back a little bit to magnetic dipoles. Now we're not actually going to be calculating the magnetic field of dipoles because it is somewhat complicated. So we're sort of just going to be seeing their qualitative form. Now, just like in the case of electric dipoles, magnetic dipoles sort of look similar, and we have an idealized dipole and then a physical dipole. So here's the magnetic field for like an ideal magnetic dipole. So you can imagine that as a bar magnet where the two poles are, close, like on top of each other, so infinitely sort of close together. Just like in the case of the electric dipole where we had that positive and negative charge and there was essentially zero separation between them. So obviously in real life we can't have that. So it's the same thing with magnetic dipoles. So we do have some cases where something approximates a magnetic dipole. One case is a current loop. So as we saw a little bit yesterday, if we have, let's say a current loop, so here, this circle means that something's coming out of the page, and again, the cross means it's going in. So we have like a current loop that's sort of shaped like this, where the current is coming out of the page here and then going back into the page there. So when we have a current loop like this, it will create a magnetic field that loops around sort of on either side like this, and then goes back out and comes in at the bottom here. So you can see these two are very similar. This is sort of like the physical realization of this perfect dipole. Then also solenoids. So when we see solenoids more in the later half of chapter 28, a solenoid is just a bunch of coils stacked on top of each other. So when we did those current carrying wires yesterday where we had like 250 turns of the coil and they were all stacked on top of each other, that was a solenoid. So a solenoid also behaves like a magnetic dipole approximately when you're far away from it. So we'll have a magnetic field that also sort of looks like this. And we'll talk more about solenoids when we do Ampere's law. And then also bar magnets look like a magnetic dipole. So we can see that magnetic dipoles will create a magnetic field. And that's because the charges that make up the current are moving. So since moving charges can create a magnetic field, that's where the magnetic field of a magnetic dipole comes from. Now, this is also how bar magnets work. So we said in an earlier lecture that it might seem like for a bar magnet, where is the charge that's moving? If you're holding a bar magnet, it's obviously not moving. So what is moving? What charges are moving to create that magnetic field that you obviously have with a bar magnet? And the answer is the electrons themselves in the iron. So as you can see here, if we have just a piece of iron, the electrons that are in the iron, so each molecule of iron has electrons around it, and those electrons are spinning, and that creates a magnetic dipole moment for the electron. So initially they're all spinning in different directions, and their magnetic moment for each electron, so imagine each one of these is the magnetic dipole moment for an electron, they're all spinning in different ways. And then when we have a bar magnet that's actually magnetized, those electrons have all aligned so that they're spinning in the same way, and their magnetic dipole moment is pointed in the same way, so you create a net magnetic field that looks like just a really big dipole then. And there's a couple different ways you can make the electrons in different materials all align in the same way, have all their magnetic dipole moments aligned in the same way. You can take a material and put it into a very strong magnetic field, and that will align all of the electron magnetic dipole moments. Or you can heat them up, you can heat certain materials up and it will do the same thing. So there's a couple different ways to magnetize materials, but the end result is that you have all of these electron magnetic dipole moments all aligned in the same way, and that creates then a net dipole moment, and then you get a magnetic field from that dipole. Now you might say, well, how does the electron, what's actually creating the magnetic dipole moment for the electron? So you can think of the electron as a sphere, and it's spinning. So it has some charge of negative E spread out on this sphere. And since we have this charge of this sphere of charge spinning, that will create a magnetic dipole moment in the direction according to the right-hand rule. Now, this is obviously not exactly what's happening, since in our current understanding, the electron is actually a point particle, and the radius of the electron is less than 10 to the negative 22 meters. So this is the upper bound that we have put experimentally on the radius of an electron. So it's obviously extremely small. So the radius has to be smaller than this. And we treat the electron as a point particle in quantum mechanics. In all modern physics, we treat it as a point particle, which means it has no radius. So this is sort of like a weird quantum mechanical effect of how we have formalized particle physics and quantum mechanics, is that these point particles have like an intrinsic spin to them, even though they're not really spinning. They have like an intrinsic spin and an intrinsic magnetic dipole moment. So I know that sounds like a little weird, it is, but that's how magnets work basically. And this is a fundamental property of all elementary particles. So electrons, quarks, they all have this fundamental spin to them. And that's part of the way that we categorize particles. And one of the physical effects of this that's actually useful is this 21 centimeter line. So the 21 centimeter line happens because in neutral hydrogen, so hydrogen is the most abundant element in our universe. There's hydrogen gas, everywhere in galaxies. So in hydrogen, you have the proton here, and the proton will have its own magnetic dipole moment. And then the electron will also have its magnetic dipole moment. And these magnetic dipole moments, since they're creating very tiny magnetic fields, since the proton is positively charged and the electron is negatively charged, they'll create these magnetic fields that will interact with each other within the atom. And depending on how basically the magnetic dipole moments are oriented within the atom, it will either lower or raise the energy of that electron. So what happens is a hydrogen atom is made up of one proton and one electron. So the ground state of the electron in the hydrogen atom actually splits into two sort of sub-levels that are separated by a very, very, very small amount of energy. So we have 10 to the negative 6 electron volts here. So this is a very, very small amount of energy. And it corresponds to a photon. So when you have an electron that jumps from this sublevel down to this sublevel, it will emit a photon with a wavelength of 21 centimeters. And we can look for that with our telescopes. So we can look for this photon of this wavelength, and that will tell us about the structure of galaxies. So we actually use this to image our own galaxy, and this was actually how we discovered that the Milky Way was a spiral galaxy. So here, this is all of the hydrogen that is in our Milky Way. So you're kind of looking at the Milky Way, like, from our position, which is out on one of the spiral arms. So we can actually image galaxies very well this way. And this is looking at a faraway galaxy, so this is not our own galaxy. And you can see that if you're just looking at it with visible light, you can't really see that much. You see some little blobs, and you can see that this one's a spiral, but that's really it. But if you image it with this hydrogen 21 centimeter line, you can see a lot more detail, and you can really see how these gases are spread out in the universe. So that's just one real-world use of these magnetic dipole moments for subatomic particles. All right, now let's start calculating actual magnetic fields. So we saw in our last chapter that only moving charges will feel a magnetic field from our Lorentz force law. We can see that if the velocity is 0, then the magnetic force is 0, and our charge feels no magnetic field. And it's the same thing with creating a magnetic field. If you have a charge that is stationary, it will not produce any magnetic field. Only moving charges will create a magnetic field. So in the case of a point particle with a velocity v will produce a magnetic field given by this equation. Now, we're just going to take this as a given. You can derive this from Maxwell's equations, but that's way beyond the scope of our course. So this is derivable from Maxwell's equations, but we're not going to do that, so we can just take this as a given. So a couple things to note here. we have this constant mu naught. So mu naught is the vacuum permeability. It's kind of like just the magnetic analog of epsilon naught, and it's equal to 1.256 times 10 to the negative 6 newtons per ampere squared. Q is the particle's charge, so that could be positive or negative. V is the velocity, it's a vector. R hat is the unit vector from the source point to the field point. Now we'll talk about that more in a second, but it's also very important to realize that this is a unit vector. So this vector has no magnitude, or it has a magnitude of 1. So when we do calculations, you have to be really careful that this always has magnitude 1. And then R squared is just like with the electric field, it's just the distance from your charge to whatever point you're measuring the magnetic field at. And it's important to note that the magnetic field is still R squared, and that's because really electricity and magnetism, like we said, are the same force. So we're going to have sort of the same form with that 1 over R squared that's so important. So let's just clarify source point and field point a little bit. So the source point is the source of the magnetic field. So if we have some, let's say, charged particle here, and we want to measure the magnetic field out here, this is our source point, and this point out here is our field point. So that means that that R hat, this is the distance R, and this is just a unit vector R hat in that direction. So R is a distance, and R hat is just a unit vector with magnitude 1. All right, so let's do an example with this first. So here we have 2 protons move parallel to the x-axis in opposite directions. So let's just draw this. So we have, we'll have our y direction, our x direction, and then our z direction will be coming out here. So let's just say our first charge is down here. So we have 2 protons. We'll say this is Q1, and this is Q2. So they're moving parallel to the x-axis, but in opposite directions. So we'll say Q1 is moving this way, and Q2 is moving this way. Okay, and they have the same speed v. So at the instant shown, find the electric and magnetic forces on the upper proton due to the lower proton and compare their magnitudes. So we have our lower proton and our upper proton, and they're moving in opposite directions. Okay, so we want to find both the electric and magnetic forces. So we want to find first the electric force on Q2 due to Q1. So we can just use Coulomb's law for that. So the electric force on charge 2 due to charge 1 will just be Q1, Q2, 4 pi epsilon naught. And we'll say the distance between them is d. So d squared. And the direction of this force is directed in the positive y direction because they're both positive charges, so they're going to want to repel each other. So this charge is going to be exerting an upward force on charge 2. So this is in the positive y hat direction. Now let's look at the magnetic force that Q1 exerts on Q2. So this is the electric, and now we'll look at the magnetic. So we're going to need the Lorentz force law. So we have QV cross B. So now this is important because which V and which B do we use here? So to find the magnetic force on Q2 due to Q1, that means it's the magnetic field due to Q1. So this is the magnetic field due to Q1, but the charge that's feeling the force is Q2. So this Q and this V are both Q2's charge and velocity. So this is Q2 and V2. So now we want to find the magnetic field due to the first charge at the location of the second charge. So we need to use the formula we just had. So B1 is equal to mu over 4 pi times QV cross R over R squared. So now since we're looking at the magnetic field due to Q1, this charge and this velocity are both charge 1's charge and velocity. And then this distance is going to be the distance to the point where we're measuring the magnetic field, which is up here at the location of charge 2. So let's write this out. So we have mu naught 4 pi. Now they're both positive. Now the charge of Q1, we'll just say Q1 times its velocity. And its velocity, let's do this cross product. So its velocity is V1 in the positive x hat direction. And then r hat is the direction from Q1 to the location where we're measuring the magnetic field, which is up here. So this is in the y hat direction. Remember, r hat is just a unit vector, so it's just in the y hat direction. So this cross product ends up being V1 in the z hat direction, because x hat cross y hat is z hat. So we have Q1 V1 over r squared in the z hat direction. Now the distance is, the distance is just d squared, so I'm going to replace r squared with d squared down here. Okay, so now I can plug this magnetic field back in here and find the total force on Q2 due to Q1. So let's just rewrite that over here. So we had Q2 V2 cross B1, and B1 was mu naught over 4 pi Q1 V1 over d squared in the z hat direction. Okay, all right, so now let's look at this cross product. So when we plug in V2, so V2 is in the negative x hat direction, right? Because we said Q2 is moving to the left, so that's in the negative x hat direction. So when we take x hat, negative x hat, crossed into z hat, so this cross product, we're going to have negative x hat crossed into z hat, and negative x hat crossed into z hat is positive y hat. So that's because if you do your little circle here, if we ignore the negative sign for a second, we would have x hat crossed into z hat is going the opposite way of your little arrows. So if you do x hat crossed into z hat, that would normally give you a negative y hat, but since we already have a negative out here, we have a negative, which is a positive. So this is positive y hat. So now we can just multiply all these things together, since now we know the direction and they're perpendicular, so we don't have to worry about that sign. So we have Q2 V2, then we have times the magnetic field of B1, so we have mu naught 4 pi Q1 V1 over d squared, and this was all in the positive y hat direction. Now the charges have the same magnitude, so we can just say that Q1 and Q2 are both just Q. So let's just say Q squared. They're moving at the same speed, so we can just call this V in both cases. And we have d squared, and let me write my mu naught over 4 pi out here. And this is in the y hat direction. Okay. So this is our magnetic force on charge 2 due to charge 1, and our electric force was over here. So now it wants us to compare their magnitudes. So we're just going to take the ratio of the magnetic force over the electric force and just see what that comes out to. So let me just make this a little bit smaller. So let's just see what FB over FE is equal to. So FB was mu 4 pi Q squared V squared over D squared, and the electric force was Q1 Q2, which since they're the same charge, we can just rewrite that as Q squared. So we have Q squared over 4 pi epsilon naught D squared from Coulomb's law. So we've got Q squared 4 pi epsilon naught D squared. And now we can see this D squared and this D squared cancel. We have a 4 pi and a 4 pi that cancel, and then we have a q squared and a q squared that cancel. So what we're actually left with is epsilon naught times mu naught times v squared. So epsilon naught times mu naught is actually very significant because the speed of light is given by the square root of epsilon naught times mu naught. So this is actually 1 over the speed of light squared. So now this is very interesting because what this tells us is that the magnetic force that charge 2 feels will always be less than the electric force that it feels from charge 1, unless it's moving at the speed of light. So this magnitude will be equal to 1 when this velocity is equal to c. So when these two protons are moving at the speed of light, then the magnetic force will be the same as the electric force. Otherwise, it will always be less. Now, since protons have mass, they can't actually move at the speed of light. So the magnetic force and the electric force will never be equal. The magnetic force will always be weaker. And this is a general thing that we're going to see as we do more magnetism. The magnetic force is very weak compared to the electric force. And it's weaker by a factor of c. So we'll see that more later. All right, so let's just rewrite this. So this is very, like I said, very, very important. Remember that the speed of light is given by 1 over the square root of epsilon naught times mu naught. And this is because, like I said, the electric and magnetic field are really not two separate fields. They're just two sides of the same coin. It's the same field. So they both are electromagnetic waves that propagate at the speed of light. So that's why the electric constant and magnetic constant are both connected then to the speed of light. And in 7e, you'll see that the electric and magnetic field obey the wave equation, which is an equation that all waves obey. And it tells you that something is a wave, and it tells you what velocity it's moving at. And from Maxwell's equations, so just from his 4 equations, you can derive a wave equation, and you can see that both the electric field and the magnetic field are both waves that travel at the speed of light. So all of that is contained just in Maxwell's 4 equations. All right, so let's move on now. So just like the electric field had the superposition principle since it was a vector, obviously the magnetic field is going to obey the same thing. So since the magnetic field is a vector, the total magnetic field anywhere will just be the vector sum of all of the constituent magnetic fields. So that means that we can use the equation that we just saw to find a formula for the magnetic field generated by some current carrying wire, since current is just a bunch of charges together. So if I have a current carrying wire, so let's say it has some cross-sectional area A, it has some length L, and we have some charges in here, and they're moving with drift velocity Vd. And they've got some density N. And this is our cross-sectional area here. So just our usual current carrying wire there. All right, so if I want to write the total magnetic field for this piece of current carrying wire, I can just write B is equal to mu naught 4 pi. And the total charge in this piece of wire is going to be the charge on each particle times their density times their the volume that they're in, the volume of this piece of wire, and then times the velocity, and then I have crossed into r. So then this is all over r squared. And now if this is just some little like differential element of wire, I can rewrite L as just dl since I'm going to want to integrate. So I can rewrite this as qn vd a, and then I have dl cross into r hat, where now this is my vector here. Since Vd and dl are going to be in the same direction. So I can rewrite this now as my current, right? So remember, this is the expression for current. So I can rewrite this whole magnetic field now as mu naught over 4 pi I dl crossed into r hat over r squared. And so this will give me now the expression for a magnetic field due to any length or piece of current carrying wire. And so this is called the Biot-Savart law. Since they're French, this is pronounced Biot-Savart. So don't go saying like Biot. It's Biot-Savart. So we're going to be using this a lot. And again, a couple of things to keep in mind. I is the current in our wire, and I is not a vector. So this is just a constant here. dl is our vector. So dl will always be in the direction of the current, but that's really our vector there. Then r hat, again, is just a unit vector, so this always has magnitude 1, and it's the direction from our little current element to the point where we're measuring the magnetic field. And then r is just the distance from our wire to wherever we're measuring the magnetic field. Okay, so let's use the Biot-Savart law to find the magnetic field due to a finite wire. So we have a finite wire along the y-axis from negative a to a. And we want to just find the magnetic field, not everywhere, but just along this center axis here at some point along this x-axis. So this is going to be very similar to when we did the electric field for a finite wire, but it's a little bit more complicated with the magnetic field since we have that cross product. So let's see how this works out. So let's first write our Biot-Savart law. So we've got the magnetic field is mu naught 4 pi. We're going to integrate I dl cross r over r squared. So luckily r itself, just the distance, is easy to find because it's just going to be the distance from every point of our current carrying wire to this point P out here. So this distance is just going to be our x coordinate of point P, and then wherever we are along the wire here, y. So this is our r squared, it's just x squared plus y squared. And then our dl is also easy to find, luckily. So dl is just going to be dy since our current is along the y-axis. So dl is just dy. Okay, so now let's worry about this cross product. So let's we'll rewrite this as a sine. So dl, the magnitude of r is just 1, or r hat rather, and then we have sine of the angle between them. So dl is in this direction since it's in the same direction as the current. So dl is going up in the y hat direction, but r hat is always changing direction depending on where you are along this wire. And this cross product will dictate or tell us what direction our magnetic field is in. So we can kind of use the right-hand rule a little bit. So if you put your hand in the direction of the current and then sort of turn your hand down into the direction of r hat. So if you have your current going up like this and then r hat is sort of directed downward like that on the page, you curl your hand in the direction of r, and you'll see your thumb is pointing into the page. So obviously it's a little hard to do over video, but try it and you'll see your thumb is pointing into the page. So that is true at every point along this wire. If you do that down here, the same thing's going to happen. Your thumb will be pointing into the page. So that means your magnetic field is going into the page from every point here. So luckily we don't have to worry about x and y components canceling, but we do just have to worry about this sine phi angle from the cross product. So how do we figure out what this sine phi is equal to? Well, phi is the angle between I and r hat, which is given by this. And since we know that this is a right angle in here, so since we know that this is a right angle, or rather, it's easier to think about it, since we know that this is a straight line, these two angles here have to add up to 180, which is pi. So those two angles have to add up to pi. So phi plus what is equal to pi? Well, it's going to be phi plus pi minus phi. So we can see it, I'll write this as x. So this angle is pi minus phi. So now we can use a trig identity. So just one of the trig identities is that sine of pi minus theta or phi is the same thing as sine of phi. So that's just a trig identity. So we can just look at this triangle in here and figure out, okay, well, what's the sine of this angle? And it will be the same as the sine of this angle. So sine of this angle is opposite over hypotenuse. So that will be x. So sine is opposite over hypotenuse. So we have sine of phi is equal to x over x squared plus y squared square root. Okay, so now we have pretty much everything. So let's plug all of this into our formula. I'm going to factor out my I out here since it's just a constant. We're integrating from negative a to positive a since it's just a line. And then we have dy from the dl. We have x squared plus y squared from the r squared. So this is here. And then from the sine, we have x over x squared plus y squared to the 1/2. So we can see that we're going to get that 3/2 again, just like in the case of the electric field. So this is our integral. So let me just make that 3/2 a little bit clearer. So this integral, again, you would have to either do a trig substitution, which I don't expect you to do, or just like look it up, plug it into Mathematica. So we can just plug this into Mathematica or look it up in a table of integrals. And this comes out to, so when you evaluate this, you get 2a over x squared plus a squared. So then we just have the mu naught. So let me just write this as b. So we have mu naught I 4 pi over times 2a x squared plus a squared. And this is into the page. So this is our magnetic field. All right. Now, what we can do with this is we can actually use this to find the magnetic field of an infinite wire. So an infinite wire would have A and negative A extend to infinity, right? Because if you take this infinitely far in the y direction, these will both go to infinity. So what we can do is we can, if we take the limit as A goes to infinity of our previous equation, so the limit of this as A goes to infinity will simplify to 2a over x, and then this term here goes to just a. Since a is much bigger than x, it will be a squared square root, so that just goes to a. So this term just simplifies out to 2 over x. So our magnetic field for an infinite wire is mu naught I over 4 pi times 2 over x, which we can just rewrite as mu naught times I over 2 pi x, where x is the distance from our wire. Now, we're going to do this a simpler way that doesn't involve taking a limit in our next lecture when we do Ampere's law. But this formula is very, very important, and we're going to be using this a lot. So the magnetic field due to an infinite current carrying wire is given by mu naught times the current in that wire, and then divided by 2 pi r, where r is the distance from the wire. Now, for a current carrying wire, we can use a slightly modified right-hand rule to figure out what direction the magnetic field is going in. So for an infinite current carrying wire, the magnetic field curls around the wire, and we'll see this also next time. This is our last Maxwell's equation tells us this. So if we're looking at a magnetic field, so again, this x here means that the wire is going into the page, so we're looking at a wire that's going sort of like away from us like this. The magnetic field we see will be curling around this wire in a clockwise direction. And that will happen, that's the case for every wire. The magnetic field curls around it in those concentric circles. And the right-hand rule for wires or cylindrical coordinates, it's a little bit easier because you only have two things to worry about. So for the right-hand rule here, to figure out what direction the magnetic field is going in, you would just point your thumb in the direction of the current, and then the direction that your hand curls is the direction of the magnetic field. So in this case, if my wire is going into the page, I just point my thumb into the page, and then my hand I can see is curling downward in the clockwise direction, and that tells me the direction of the magnetic field. Or let's say the current was coming out of the page. So if the current was coming out of the page, I would point my thumb like towards me. It's coming out of the page, and then I see that my hand is curling in this direction now, which is in the counterclockwise direction. So if the current was coming out of the page, the magnetic field would be in the opposite direction. But in both cases, it's curling around that wire. So here's just a little picture. So you point your thumb in the direction of the current in either case, and then your hand just curls in the direction of the magnetic field there. Okay, so let's use this now to find, we want to find the total magnetic field at each of these 3 points, P1, P2, and P3. So we want to find the magnetic field at P1, P2, and P3. So we have a wire here where the current is going out of the page, and here the current is going into the page. Remember, circle means the current's coming out. X means the current's going in. So we've got two wires, one coming out of the page, one going into the page. P1 is over here. It's, we'll just call this like our origin. So we've got like a the Y direction there, X direction here. So P1 is a distance of 3D in the negative X direction. P2 is right at the origin, and then P3 is a distance of 2D from the origin in the positive X direction. So let's find the total magnetic field at each of these points. So let's start with P1. So P1, let's find the magnetic field from the first wire. So from wire 1, I'll call that B1. So let's just find the magnitude first, then we'll worry about the direction. So the magnitude is just going to be given, I'll write this, let's write our formula for a wire. So this is our formula for a wire. So for the first wire, we have mu naught I, they both have current I. Then we have 2 pi, and the distance from wire 1 to point P1 is 2D, right? Because point P1 is 3D out here, and then wire 1 is located distance D. So this distance is 2D. So we have 2D. And now what direction is the magnetic field in? Well, we have to use our right-hand rule. So the current is coming out. So if we point our finger, our thumb, out of the page, at point P, our hand is pointing downward. It's curling downward. So at point P, our magnetic field from wire 1 is downward, which is in the negative y hat direction. Now let's look at the second magnetic field from wire 2. So we're going to have the same thing, mu naught times I, 2 pi, and then the distance here now, we have 3D and then another distance of D, so that distance is 4D. And now what direction is the magnetic field pointing in from wire 2? Well, wire 2 is into the page. So we have to point our thumb into the page, and then if we curl our hand all the way around, by the time so we have to curl it sort of like a whole, like almost 360. By the time we get back to P1, our hand is pointing upward. So since we're moving in the clockwise direction, when we get to P1, the magnetic field from the second wire is upward. So this is in the positive y direction. So now we just add both of these together, and we get B total. This comes out to mu naught I 2 pi 4D, and then this is in the negative y hat direction. So this is our magnetic field at point 1. Okay, so our all right, now let's look at point P2. So P2 is in the origin here. So for P2, the magnetic field from wire 1, we're going to have mu naught I 2 pi. The distance is just d now, so that distance is d. And the direction, wire 1 is coming out of the page, so we have to point our thumb out of the page. And then it's going counterclockwise, so when we get back to P2, we have to go like sort of around underneath. When we get back to P2, our thumb is pointing, or our hand is pointing upward. So this is in the positive y direction. Now from B2, we have mu naught I over 2 pi. Again, the distance is d, so we just have d there. And the direction, we point our thumb into the page, turn your hand around. When your hand gets back to P2, you're going up again. So that's also in the positive y hat direction. And then when we add these two together, we get just twice 2 mu I over 2 pi d in the positive y hat. So it's just twice the magnetic field from each. Okay, so that is our magnetic field in point P2, at point P2. Now let's find our magnetic field from point 3. So at point P3, the magnetic field from the first wire is mu naught I over 2 pi. The distance is d, and then we have another d to get here, or just d plus 2d. So that's going to be 3d. And the direction, we point our hand, our thumb out of the page, and when we get to P3, we see that our hand is pointing upward. So this is also in the positive y hat direction. And then B2, we have mu naught times I, 2 pi. Now, the distance from wire 2 to P3 is just d. So this is just d here. And then the direction, we point our thumb downward, our hand curls this way, and we're going downward at point P3. So this is negative y. So this comes out to, when you add these up, mu naught I over 3 pi d in the negative y hat direction. So that's the magnetic field at point P3. Okay, so I know that the right-hand rule with this stuff can be very confusing, but really, like, just try it out and practice it a lot, and eventually you'll get the hang of it. Okay, and then the magnetic field also, so if you plotted out the whole magnetic field for this setup, it would look sort of like a dipole. So it would look like this, as we saw in the beginning of the lecture. Okay, so now we're going to go on to the force between two wires. So we want to find the magnetic force between two infinite current carrying wires. Now the first case we're going to look at is if the wires are carrying current in the same direction. So we're actually going to need our formula that we did yesterday. So we're going to need both our formulas now. So remember, the force on a current carrying wire was IL cross B, where this is some external magnetic field the wire is placed in. This is the length of wire that you're looking at, so maybe just this length here where these wires both go on for infinity. And then I is the current in that wire that's feeling the magnetic force. So let's say I want to find the force on wire 2 due to the magnetic field of wire 1. So I need the current in I2, the length of wire that we're looking at on this second wire, and then this is going to be the magnetic field of wire 1. So this is the force on wire 2 due to wire 1. So we know the magnetic field of a infinite wire is mu naught times I over 2 pi r. So that's the magnetic field I'm going to be plugging in here, where this is the current in wire 1. So if these two wires are a distance a apart, that means that I'm going to replace r here with a because we're looking at the magnetic field from this wire at the location of this wire. So that's going to be a. And then the cross product will come out to 1, so the sign here will end up being 1 because this will be 90 degrees. So the way we can figure that out is that if I put my thumb in the direction of current 1, and then I turn my hand in the direction of the magnetic field, I'll see that the magnetic field of this wire is coming out, sort of like out of the page here at this location. So this is the magnetic field of current 1 at the location of current 2, and it's coming out this way. So then if I look at this cross product here, L for current 2 and B are perpendicular. And if I do the right-hand rule again, so I put my hand in the direction of current 2, which is in this case like sort of to the right, and then I curl my fingers in the direction of the magnetic field of current 1 at that location, I have my thumb pointing downward. So the force is actually directed downward towards that other wire. So if I plug all this in, let's say this is some length L that we're looking at. And then B1 I'm going to replace with the magnetic field. This is downward. And I can rewrite this as mu naught I1 I2 over 2 pi a. And what I can do is I can write the force per unit length. Since these two wires are infinite, it obviously doesn't make sense to talk about the total force because that would be infinite. And since infinite wires are sort of unphysical, we don't want infinite forces. So we're just looking at the force per unit length so we get a nice finite answer. So we're just looking at equal segments of length L of each wire. So the force per unit length that this wire down here exerts on this wire up here is attractive. So this force is downward, like we said, towards current I1 or wire 1. Okay, so we can see now if we did the same thing where we reversed it and we wanted to find the force on current 1 from current 2. Now I highly recommend that you do that yourself and see that you can use the right-hand rules correctly because there's two different right-hand rules we use in this problem. So check for yourself, redo this problem, but find the force on 1 due to current 2 and make sure that you get the exact same magnitude, but the force should be upward because they should be equal and opposite forces because they're attractive. So try that. I really highly recommend you try that yourself. That's a good way to check that you understand the right-hand rules properly. So you should get same magnitude, force per unit length, but an upward force on current 1 due to the magnetic field of current 2. So what if the currents now were in opposite directions? So what if my currents now, I had I2 here, and then I1 going in the opposite direction. There's still a distance A apart. So now I'm going to rewrite my equations. So now I want to still find the force on wire 2 due to wire 1. So this is the current in wire 2, the length of wire 2, but we're looking at the same lengths for each, and then the magnetic field of current 1. So the magnetic field of current 1, I know the magnitude, is just going to be mu naught I over 2 pi a again. But the direction here we have to think about. So if I point my thumb in the direction of current 1, which in this case is to the left, my hand will be into the page at the location of I2. So B is into the page here. So let's write that, into page. So this is into the page. So now when I do this cross product, I have current 2 is going to the right. So I point my hand in the rightward direction, in the direction of current 2. Then I turn my fingers in the direction of the magnetic field of current 1. So that's into the page. And I see now that my thumb is pointing upward. So the force is actually upward. So if I rewrite all of this out, so I have I2 times some length, mu naught I1, and then I have 2 pi A. I can rewrite just the force per unit length, and that's going to be mu naught I1, I2 over 2 pi A, and that's upward on the second wire here. So this is a repulsive force. So again, I highly recommend that you try the force on current 1 due to current 2 and check that you get a downward force with the same magnitude because they're repulsive. So the forces are going to be equal in magnitude, again, opposite in direction. So this is a repulsive force. So here we can write the force per unit length of 2 infinite current carrying wires. So current 1 and current 2 are just our 2 currents. R is the distance between our wires. And now if the currents are in the same direction, our force will be attractive. And if our currents are in opposite directions, our force is repulsive. So this is a little bit confusing because it's sort of opposite what we've been seeing with charges and magnetic poles, where like currents attract and opposite currents repel. So it's a little bit confusing there. But like I said, just try these a bunch with the right-hand rule, and eventually, the right-hand rule will make sense a little bit. All right, so let's do an example with this. So here we have 2 straight parallel superconducting wires that are 4.5 millimeters apart. They carry equal currents of 15,000 amps in opposite direction. What force per unit length does each wire exert on the other? So our force per unit length was mu naught I1, I2 over 2 pi, and then the distance between them. So let's just plug in our numbers. So mu naught is, we'll say 1.2 times 10 to the negative 6. I1, they're both 15,000 amps, so we'll say 15 times 10 to the 3, and then 15, 10 to the 3. And then we have 2 pi, and the distance between them is 4.5 times 10 to the negative 3. Okay, and this is the force per unit length. So we can plug that into our calculator, and we get 1 times 10 to the 4 newtons per meter. So this is the force per unit length. And since these currents are traveling in opposite directions, they will repel. So it's repulsive. All right, so now we have one more example. So for this one, we want to find the magnetic field. Due to this current loop, so we have a current loop of radius A, and we want to find the magnetic field out here at some point P, which is along the x-axis, so along the axis of our current loop. So what is the magnetic field here? Well, we're going to have to use our Biot-Savart law and integrate. So let's write that first. So we're going to have mu naught over 4 pi. Then we're going to do I dl cross r hat over r squared. Okay, so let's start figuring things out here. So let's do r first. So r, we can see that from any point along our loop, it's going to be a distance x away, and then this is our radius. So this distance from every point on our loop to the point P is just going to be a squared plus x squared, or x squared plus a squared. So we're going to have x squared plus a squared square root. All right, so r was easy enough. Now we have to figure out this cross product first. So let's figure out this cross product. So dl cross r. So we can see here that dl is like tangent to our loop at every point around our circle, and r is in this direction. So these vectors are perpendicular, and the sign here is going to be 90. So we'll have sine of theta is equal to 90. So we don't have to worry about this cross product really. So I'm going to just rewrite, I'm going to pull out my current, and then I have this cross product we said just comes out to basically dl over r squared. So since r hat is a unit vector and we don't have to worry about a cross product yet. But let's look closely at what the direction of the magnetic field is. So dl cross r, when we do this cross product, or if you do your right hand rule here, if you put your hand in the direction of the current and then sort of curl your finger in the direction of r hat, you'll see that your thumb is at an angle. So B is at an angle here, and this is a right angle between r hat and B, but B is at an angle to our y-axis. Now, you can do this for every single point around your circle, and you're going to see that all of your y components are going to cancel. So just like in the case of the electric field, only our horizontal components along this direction are going to remain, and each y component here is going to be offset or canceled by the y component of the magnetic field from this point of charge down here. So our y's will cancel and we'll be left with only the x component. Okay, so what I'm going to do is I'm just going to draw a new picture. So let's look at it like this. So this is our x direction, this is our y direction, this is our point P, and our wire loop is sort of, it's like this. So we're looking at it like head on. So this is negative a and positive a. So we're looking at our loop head on. R is like this. So this is R. And then DL for this point would be like sort of coming out of the page at us. So B, since the cross product has perpendicular vectors, B is perpendicular to the direction of R hat. And what we're looking for is the X component here. So this is our X direction. Oops. So we're just looking for the X component of our magnetic field, since the Y components cancel. We're just looking for this component here. So this we can see is going to be cosine theta, since it's adjacent to our angle here. So we're going to need to, again, pluck out that X component using our cosine theta. Now, unfortunately, we don't know what this angle theta is yet, but we do know some other things. So we know that this is a right angle, and we know that this is a right angle because R and the direction of R hat and B have to be perpendicular. So if we know that, and we know that this is a straight line, it has to add up to 180 degrees. So we can figure out this angle in here. So that angle in there, so we have pi for the straight line, so it's pi is equal to theta plus the pi over 2 from the right angle here, plus whatever this angle is, so I'll call that like W. Okay, so then that means that that unknown angle is equal to pi minus theta minus pi over 2, which gives us pi over 2 minus theta. So this angle here is pi over 2 minus theta. Now, since I know that a triangle will also have 180 degrees, I can figure out this angle over here too. So we'll say again that pi is equal to pi over 2 minus theta plus the pi over 2 here from that right angle, and then we'll call this maybe like z. So this angle is z. So we can solve for z, and we get pi minus pi over 2 plus theta minus pi over 2. So that is equal to theta. So this angle here is also theta. So that means that I can just take the cosine of this angle, and that will be the same as the cosine of this angle. So the cosine of this angle, so let me just rewrite what I had here. So we're going to have the same integral, but now we have cosine theta. So I can rewrite cosine theta is the adjacent side, so that is a over r, which is a over x squared plus a squared square root. So now I can plug everything in. I have a over x squared plus a squared. Then I have the 3/2 from this r squared, because that's x squared plus a squared. So I have 3/2 on the bottom here, and then I'm integrating with respect to dl. So my integral actually, so dl, just like in the case of the charged ring, my variable of integration has nothing to do with x or a. So I'm just integrating around a loop. So I can just multiply by the circumference of that loop, and that's my integral. So this integral, all of this is a constant. And there's nothing to integrate. I just integrate over that loop from 0 to 2 pi a, and that just gives me 2 pi a. So overall, let me just rewrite all of this out again. So my magnetic field along that axis was mu naught I over 4 pi. Then I had a over x squared plus a squared 3/2, and then I just had a 2 pi a. So now I can simplify this a bit, and I'll be left with mu naught over 4 pi. I have 2 pi a squared, x squared plus a squared 3/2, and I can simplify out my, oops, I left my current. Okay, so then I'll have a squared times the current, then I have 1/2 on the bottom, then I have x squared plus a squared 3/2, and this was all in the x hat direction. Okay, so this is my total magnetic field now along the axis of that ring due to my current carrying ring. Okay, so that's it for today. Don't worry too much. When we do part B, we will be doing Ampere's law, which is a much simpler way to find magnetic fields for highly symmetric current distributions. So we won't be doing any more integrals like this in the rest of chapter 28. All right, so that's it for today, and I will see you guys next time.